Hi, it's time for another math easy solution. Time to discuss a very interesting video on modeling with differential equations, and then basically look at population growth to illustrate more on differential equations, and also go introduction basically on this whole concept of modeling, and as well as go over what differential equations are. Basically, perhaps the most important of all applications of calculus is to differential equations. So yeah, this video is going to be a lot of reading out here. Basically, when physical scientists or social scientists use calculus, more often than not, it is to analyze a differential equation that has arisen in the process of modeling some phenomenon that they are studying. Yes, and although it is often impossible to find an explicit formula for the solution of a differential equation, so it is very, a lot of these equations are hard to find explicitly, and we will see that graphical and numerical approaches provide the needed information to solve these, or estimate them using approximate analysis. And basically the process of modeling involves formulating basically a mathematical model of a real-world problem, either through intuitive reasoning about the phenomenon or from a physical law based on evidence from experiments. So again, a lot of this is why it's really applicable to the physics and science, because we are looking at those experimental data and then from there trying to develop mathematical models. Basically, the mathematical model often takes the form of a differential equation, and a differential equation is an equation that contains an unknown function and some of its derivatives. So basically that function includes its derivative, and that's why it's called a differential equation. So circle that better. So this is not surprising because, in a real-world problem, we often notice that changes occur, and we want to predict future behavior on the basis of the current values and how they change. Basically, the rate of change, or however things change, depends on what the value is currently. And that's often is the case in the real world. And one example of how differential equations arise when we model physical phenomenon is in population growth. And here we're going to look at some models of population growth, and in fact we'll go over two models, one simple and one a bit more complicated. Basically, one model for the growth of a population is based on the assumption that the population grows at a rate proportional to the size of the population. And this is a reasonable assumption for a population of bacteria or animals under ideal conditions, and then those conditions are basically such as unlimited environment, adequate nutrition, absence of predators, immunity from disease. So basically, if you just assume, let's say that there's no way of them dying off, and they just keep replicating on, and immunity from disease could include death as well if they just don't die. But even if you include death, when you ignore everything else, when you assume there's unlimited food, etc., you'll notice that, it's proportional to the size of this population, because when you have a large population, each one is reproducing, so you're going to obviously get a bigger rate of increase as opposed to very small. And often the case when it's a small population, they just don't reproduce as fast because they're just not in that constant contact as when you have more condensed large population. Anyways, let's identify and name the variables in this model. So we'll let t equals time. This will be the independent variable. So at whatever time t, we would look at population, which is, we'll write p, and that's the dependent variable. So this depends on whatever time is. So at a time, we'll look at the population, and not the other way around. Basically, that's the y-axis. So the rate of growth of the population is the derivative dp divided by dt. So our assumption that the rate of growth is proportional to the population size is written by the equation dp over dt. So the rate of change, rate of growth of population is, let's just write equals to, is proportional, so k times p, which is a proportionality constant. And again, I'll just write that down here. So basically, where k is the proportionality constant, so this is basically, again, modeling this assumption we made, which is the growth rate is proportional to the population size at whatever time it is. So this equation is in fact our first model of population growth. It is a differential equation because it contains an unknown p, so that's the function, and its derivative dp over dt. So this is a differential equation. So now that we've formulated this model, let's look at its consequences. If we rule out a population of 0, because we have nothing, it's not going to replicate, then basically the population is going to be greater than 0 for all time t. So we're not going to have a negative population. That doesn't make physical sense. So if k is greater than 0, so that we're always growing as opposed to decreasing, and again it's a constant, then this equation shows that the derivative p prime of t, or dp over dt, this is always positive for all t. So this means that it is increasing, because if this is positive, p is positive, k is positive, this is positive, this is also positive, meaning that the growth rate is increasing. So this means the population is always increasing. In fact, as p of t increases, the equation shows that dp over dt becomes larger. Yeah, and as you can see here, if this is growing and then p is growing as well, that means, and it's, since the derivative is related to the population, as this gets bigger, this number k is constant, so this just gets bigger, the rate gets bigger, and basically it just keeps increasing. So in other words, so dp over dt becomes larger as p of t increases. In other words, the growth rate increases as the population increases. And now let's try to think of a solution of the equation. This equation asks us to find a function whose derivative is a constant multiple of itself. So if you had this function p, the derivative here is just p, but then there's a constant there. So again, it's a constant multiple of itself, and we know that exponential functions have that property, and you can see that in my earlier video. In fact, if we let p of t equals to c e power of kt, then what we end up having is the derivative p of t. So the derivative p of t, that just is equal to itself right here. So this equals to c, and then derivative e to the power of kt, where k is also constant. We'll have e to the kt, and then using chain rule, add the k in front. I'll just put that in bracket like this. K e k t, which this equals 2. I'll put the c inside, so what we'll have is k and then c e k t. In other words, what we have right here is dp over dt, that's the same thing as writing p prime of t, equals to k and then c e k t, that's just equal to p of t. So there you go, that's a solution to that, to this differential equation. So thus what we have is any exponential function of the form p of t equals to c e k t is a solution to our differential equation. And in later videos I will show how there is in fact no other solution but this exponential function, which is pretty remarkable and all. So stay tuned for those videos in the near future. Anyway, so allowing c to vary through all real numbers, including negative numbers, we get the family of solutions of p of t equals to c times e to the power of kt, whose graphs are shown in the figure below, and I'll draw that like this. So if we have t, I should put this more in the center because we have negative values. Like this. This is p, and this is time t, that's population. So it's just an exponential function. So if you have a c value like that, it goes up. If you have a high one, a low one, etc. So something like this. And then on the negative side, you're gonna obviously get something like this. If we have a negative c right there. So these are functions of the population. And these are for all t values, all time, and all C values when we vary it through all real numbers. Yeah, but populations, they don't have negative values, so they only have positive values. So we are interested only in the solutions of C where it's greater than 0, so we don't have any negative populations. And we are probably concerned only with the values of t greater than the initial time t equals 0, because I'm not sure how you would work with a negative time. So now the figure below shows the physically meaningful solutions. So if we were just to look at the positives, what we end up having is p, and we basically cut off all the populations. So we have something that looks like this for that was past the 0. So something like this. Let's go slower. I think this would be a bit wider out. It would be something like that. So again, these are more meaningful solutions of the population growth differential equation. These are just looking at physically meaningful. So we only have positive time and positive population growth, or population. And also what's interesting is if we put t equals 0, what we end up having is p of 0 equals to, c, e, k, and t is 0 now. And then this goes to 1, e to the 0 is 1, so we have equals to c. So all these at time is 0, what we end up having is c1, c2. So these are just different constants, c4 over there. So thus the constant c turns out to be the initial population p of 0. So now the basically illustrate further, the differential equation we use is appropriate for modeling population growth under ideal conditions, but we have to recognize that a more realistic model must reflect that a given environment has limited resources. Yes, if we're on Earth, you can't just keep growing population unlimited. Earth isn't big enough. So many populations in fact start increasing in an exponential manner, but the population levels off when it approaches what's called the carrying capacity. We'll call it capital K, or decreases to K if it ever exceeds K like that. So this is a interesting model. An interesting observation about populations. Basically, you have limited resources, so a environment can only withstand or sustain a limited number of people or animals or whatever population you're looking at, bacteria, for example, or anything. So for a model to take into account both trends, that it does increase in fact exponentially initially, but then it tailors off up to this carrying capacity, we make two assumptions. Initially, the growth rate is proportional to p. Or in other words, what we could write is dp over dt. Well, it's roughly proportional to k over p. And we're putting roughly proportional because it's a model when we have, again, a couple of assumptions, so this is roughly what we want. And now what we want is p decreases if it ever exceeds k. In other words, what we'll have is dp over dt. The growth rate has to decrease, so it's less than 0, meaning population is decreasing. So it's less than 0, the derivative is less than 0, if the population exceeds k. And now what's interesting is a simple, a simple expression that incorporates both these assumptions is given by the equation. I'll draw that right here. So the differential equation will look at something that's pretty simple but still matches both. And in fact, if we were to write dp over dt, the derivative equals to, let's say it equals to kp, so it's proportional to this, but we'll add a factor of 1 minus p over k, capital K. So this is, I don't know why my pen was doing that. So that's capital K like this, small k, capital K, just to make sure you're not confused. Let's draw this even smaller. So small k, and then we have capital K here. So if we look at this right here, when p is greater than k, we have this greater than 1. So then we'll have a 1 minus a number greater than 1, which makes it negative. So whenever it's greater than k, you'll have it decreasing. And when p is really, really small, this goes to roughly 0. So this approaches 0 when it's small. So what we'll end up having is this roughly is equal to 1, which makes it the proportional, basically makes the derivative roughly proportional to the population size, or just Kp. And here I've written that down. Basically, notice that if P is small compared with capital K, or the carrying capacity, then P divided by K is close to 0. So if it's close to 0, if this is close to 0, we have 1 minus 0, where it's just 1. So what we'll end up having is, so then again, dP over dt is roughly proportional to Kp, or equals to Kp, like that, which is our first assumption. And now the second one, if P is greater than K, then 1 minus P over K is negative, because this P over K will be, well, greater than 1, and 1 minus a number greater than 1 is negative. So this derivative is going to be, well, negative. dP over dt is negative, so the population is decreasing. And now some interesting notes on this equation. This equation is called the Logistic Differential Equation, and was first proposed by the Dutch mathematical biologist Pierre-François Verhulst, I'm not sure how you pronounce it, in the 1840s as a model for world population growth. Just a brief history lesson on Pierre. He was born in Brussels, Belgium, and lived from 1804 to 1849, so he lived about 45 years. And yeah, he published this logistic equation in 1838 and its solution in 1845. It was a long time to find out its solution, but it was not until 1920 when this model was rediscovered by American biological researchers Raymond Pearl and Lowell Reed, who promoted its use. Also, I think I just overlooked a step. Basically, he was a mathematician and a doctor in number theory from the University of Ghent in 1825. And yeah, my calculus book says biologist. I researched up here. I didn't see that on Wikipedia, but I guess he might have been a biologist as well. Anyways, I thought it was pretty interesting. So he developed this equation, but again, it wasn't used widely until these American researchers promoted its use. And this often is the case in mathematics and classical mathematics and sciences. It usually takes a while for its popularity of whatever theorem to go widespread. So now continuing further, I will go over techniques in later videos that enable us to find explicit solutions of this logistic equation. Again, in my later videos, so stay tuned for that, or for those. Better grammar. But for now, we could deduce qualitative characteristics of the solutions directly from the logistic differential equation. So again, the explicit solutions, I'll do that in later videos, but for now we could try to roughly estimate how the graphs would look like of the solutions qualitatively by looking at that logistic equation. So we first observe that the constant functions p of t equals 0 and p of t equals k are solutions, because in either case one of the factors on the right side of the logistic equation is equal to 0. So let's just scroll back up here. So if p of t is equal to 0, so if this equals to 0, this is just 0. So then the derivative is equal to 0, which is true. So if population is 0, when you plug in p, that just goes to 0. And if k is equal to p, if p is equal to k for all values of time, you plug in k, we have 1 minus k over k, which is 1 minus 1 goes to 0. Which equals 0, and the derivative of p of t equals k is also 0. So I'll just draw that out actually, just to clarify it further. So if p of t is equal to 0, the derivative of 0 is equal to 0, and then if we plug in, let's just plug in our values. So dp, now we'll look at the differential equation. d of p of dt is equal to k times 0, that's p, and then this is 1 minus 0 over k. This just goes to 0. So this is true, this is true. So the solution, basically this is a solution of this differential equation. Now if we look at the second one, if p of t is equal to k, capital K, this is again small k, capital K, what we end up having is the derivative p of t of k as is constant, that equals to 0 as well. and then similarly dp over dt is equal to k p 1 minus k over k, which is just goes to 0. Yes, this is 1 minus 1, that equals to 0. So 1 minus 1 is 0, so we have 0. So 0, 0, and it fits. So basically the derivative of this is equal to the derivative of this differential equation. So yeah, anyways, let's just scroll back up here. In fact, this does make this does make physical sense, because if the population is ever 0 or at the carrying capacity, it stays that way. Because again, if the environment can withstand a certain amount of people, then it will withstand that in case unless there's some sort of epidemic or anything. But outside of that, it will just stay that way. And if it's 0, well, nothing's reproducing, so you just stick at 0. And now these two constant solutions are called equilibrium solutions. And again, because they're in equilibrium and nothing is changing. And now if the initial population P of t lies between 0 and k, then the right side of the logistic equation is positive. And again, just look at that. If you look at this, if population is between 0 and k, this is less than k, so 1 minus, this is going to be, well, less than 1. It's just a ratio of less than 1 where k is greater than p. So then this is positive. So we are increasing. So then dp over dt is greater than 0 and the population increases. But if the population exceeds the carrying capacity p is greater than k, then 1 minus pk is negative, because, well, this is p is greater, 1 minus a number that's going to be larger than 1, and it's negative, so dp divided by dt, or the derivative, is less than 0 and the population decreases. Yeah, but notice that in either case, if the population approaches the carrying capacity as p is approaching k, then dp over dt approaches 0. Yeah, which means the population levels off. So initially it's exponential, and then it levels off, because again, if we just look at how this function is, as you get closer and closer to k, we get closer and closer to 1. If this is closer to 1, 1 minus 1 is approaching 0. So, so we would expect that the solutions of the logistic differential equations have graphs that look like the ones in the figure below. And I'll draw these out like this. Let's say we had, this is t and that's p. Yeah, something like that. And now what I'll do first is I'll draw the equilibrium equation. So this one is already at the 0, so p equals 0. That's this right here. And now we will draw, let's just include the negative t values to be more general. So this is our p, I'll write that here actually, p equals to k line. Draw that a bit straighter. So it's just a horizontal line, and this and this, I'll drag this up here. So these two curves are our equilibrium solutions. Yeah, now our non-equilibrium solutions are just going to be, I'll draw that in red. So again, you'll have it if you look at the top of that. Let's just draw the first ones, actually, the more ones we're used to. So if we had a small population, will increase like this exponentially, and then it will approach it but never reach it as we are approaching the carrying capacity. So again, let's look at a more smaller one. So it looks something like this. Again, I'll draw this like that. So different solution when we vary, whatever constant it is. Again, we don't have the solution for it, but we are just guessing approximating using these qualitative observations that we made. So again, it's exponential, then it goes to leveling off near it, and then if we had it higher than the carrying capacity, we would again decrease, because it's always like that, and it's decreasing. As we approach it, it's getting closer and closer to 0, the derivative. So whenever the derivative is 0, it's going to be horizontal. So another one goes like that, etc. So this is how the graphs we expect them to be. And again, basically notice that the graphs move away from the equilibrium solution p equals 0 and move towards the solution p equals k. So yeah, you have this bottom equilibrium solution, and then as all these graphs approach the top one of the carrying capacity, P equals K. But then if you look in reverse time, it's going to go from here approaching the other equilibrium. So anyways, these are just how these families of the solutions should look like, and in later videos when I find an explicit solution and formula for them, you will see that this is actually the case. Anyways, that is all for today. If you learned all this pretty extensive introduction to differential equations and how we go about modeling real world problems using them, and also going about finding solutions to these differential equations or models. Anyways, all for today. If you learned, and like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.